So let me start recording. So I hope everyone is having a good semester so far. We are in the 4th week of the semester already. I can't believe it's already going to be March soon, which is just really crazy. I feel like the semester is going by pretty quickly already. So we've started talking about some intro epidemiology concepts. In last week, we started talking about measuring health and disease. We are going to continue on that and go through another example and talk about measures of morbidity today. Last week, we focused on measures of mortality. And then we will also talk about infectious disease epidemiology. And as I said in the emails, I kind of moved the infectious disease epidemiology section up. It was normally going to be after the semester, but I moved it up to give us a little more time to discuss it, but then also because we are in the middle of an infectious disease pandemic with SARS-CoV-2. And so it's relevant to talk about and how we think about some of these things in the field of epidemiology, and even how epidemiology has been used to help guide recommendations and policies. Though I will say, in the large part, a lot of the science, and as we've talked about, a lot of the science hasn't always been used to inform decisions that are being made in different areas. And that has been somewhat problematic throughout this pandemic as well. And this kind of all relates to what I said in the first week and what I've reiterated a couple of times in that public health and epidemiology, we can't separate it from politics, unfortunately, because so many things that affect our health are due to policies and who has access to what, how policies are developed, and other things. So unfortunately, sometimes that has to kind of trickle into the way that we discuss different things. So I'm going to, for a couple of reminders, so you have your first homework has a goal due date this upcoming Sunday at the end of the day. As I've mentioned before, those goal due dates mean that you can submit it anytime before the midterm. That is just when I recommend that you submit it, because early next week, I will assign your second homework assignment, and then you'll have a third one before the midterm as well. So you don't want to let the assignments and the material for the class pile up, because that will just make it more difficult to catch up and do well on the exam, on the homeworks, and on everything else that you have going on, especially because I know you all have many other classes and you have jobs and families and life going on, especially in the middle of the pandemic. So do your best to keep up on everything. And if you find yourself falling behind, or if you have questions about anything or need help with anything, please never hesitate to reach out to me so that I can help support you and ensure that you're getting everything that you need to do well and to complete the assignments in a timely manner. And then otherwise, I think most people completed the first quiz as well. There isn't one this week since I moved the schedule around, but there'll be a quiz next week that'll be on Cougar courses that will be very similar. So make sure you're keeping up to date on those. And then next week, we'll also start talking about the final project that you'll have to submit, and you'll submit small parts of it throughout this semester, and then a final version at the end of the semester, but I'll give you guidance and feedback along the way. And those are the main things for now. So just keep up to date on the material. Don't hesitate to reach out if you have any questions on anything. But before I get started on today's lecture, starting out with talking about measuring and health and disease, what questions do you have, or what do you need from me at this time? I'm sorry if you see me shaking around a lot right now. My cat is deciding that this is the best time for her to jump around on my keyboard and on my desk. So she is not letting me not pet her. So I'm just going to hold her because it's very distracting when she's hitting my hands while I'm trying to talk. So what questions, anything that you all need for now? Cool. All right. So let me go ahead and share my screen. And it's going to be, let's see. All right, so as always, while I'm talking, if you have any questions, feel free to chat them in, or feel free to unmute yourself and ask them directly. I'll do a very, very quick review of some of the things that we talked about last week, and then really jump into measures of morbidity. So for this part of the lecture, the idea is to be able to talk about the uses of measures of morbidity and mortality, why they're important in the field of public health, and why rates are important for being able to describe the distribution of disease, and to be able to compare rates of disease between populations, and so on. So we talked about a little bit last week, and you have some recorded lectures on surveillance. All of this is related to surveillance for disease. And the process of surveillance is the idea of collecting data, analyzing data, tracking patterns of disease in the population. So we can use that to inform policies, to inform resources, inform public health practice in order to protect the health of our populations. If we don't track or do surveillance on disease to understand how it's distributed and who's getting affected, then we're not able to properly develop policies and allocate resources to the people who need them the most. So surveillance is an extremely important part of public health as a whole, and of us understanding the health of the population and implementing policies and practices to protect the health of the population as a whole. And so a big part of surveillance is measures of disease frequency. Really what we're doing when we're conducting surveillance is we are tracking different rates of disease and death in the population. And we do that with some of the measures that we started talking about last week, where we started talking about measures of mortality. And so those measures of mortality include things like our crude mortality rate, our cause-specific rate, our age-specific mortality rate, infant mortality, case fatality rate, and proportionate mortality. And last week in the live session, and then also in some of the recorded lectures, we went through some examples of calculating measures of mortality in that first in-class exercise. So hopefully that gave you all a little bit of insight into how these are calculated and what goes into these calculations. And as I've mentioned before, okay, sorry, my cat is literally going crazy. As I mentioned before, the most important thing for these measures of mortality and for morbidity is your population. So who is the total population that you're doing your calculation out of? Or who is the population at risk for that particular disease? So for example, if we're doing a cause-specific mortality rate for ovarian cancer, our population at risk would only include biological women who have ovaries. And so we need to be mindful that when we are doing those calculations, that we are only including people who are at risk for that particular disease. And this is a common mistake that I see not only on exams and in the homeworks for this class, but actually a common mistake in the way that this rates and these measures of this disease frequency are misinterpreted by the media and by other people who don't understand how they were calculated. Because it's important to know, who do these numbers relate to? So if I'm talking about that cause-specific mortality rate, I need to know when that is happening, what's the year, out of how many people in the population. I need to know who my population of interest is. And so those are those three important aspects of a rate, which is when's it happening, who's it happening to, and out of what proportion of the population. And there's a question on your homework that asks you to compare the crude number of deaths in the United States between 2 different years, and compared to the rate of death in the United States between those 2 different years. And the idea behind that is to reflect on the limitations of just having a crude number of deaths. So for example, if I say in yesterday, 1,000 people died in San Diego County and 1,000 people died in Los Angeles County, that just gives me a crude number of deaths. That doesn't allow me to compare kind of apples to apples and say, okay, were there more deaths per capita or per size of the population in San Diego versus in Los Angeles? So those crude numbers have limitations in that they don't tell us anything about the unit size of the population or when they're happening or other information that's necessary to actually interpret what they mean. And so that's where these mortality rates and other measures of morbidity and mortality are useful, because they give us that information to be able to compare. So if I said that there were 1,000 deaths per 100,000 people in the population in San Diego County and 5,000 deaths per 100,000 people in Los Angeles County, that tells me that the rate of death is much higher in Los Angeles County than in San Diego County when we're comparing by population size. So it gives us a lot more information to be able to make decisions about where to allocate resources and what those numbers actually mean. So that was all last week. If you have any questions about doing some of those calculations, make sure you're comfortable with the exercise questions. Your homework questions are very similar, and you are going to see similar questions on the exam as well. And I'll tell you, and I think I've said this before, usually for homeworks, for quizzes, for all of those types of things, what I do is I just take old exam questions and I put them onto these assignments, and then you'll see modified versions of those or very similar types of questions. They're not going to be exactly the same, but very similar types of questions on the exam. So you'll always have had an opportunity to practice all of the calculations and everything that we're learning about before you get to the actual exam. Okay, so now we're going to talk about measures of morbidity. And so our measures of morbidity that we use most commonly in epidemiology are prevalence and incidence. And you all have probably heard the terms prevalence and incidence in your other classes. You've probably seen prevalence numbers given for COVID-19 and for other diseases. You've probably seen incidence discussed. And so what we're going to talk about is how they're used, why they're important measures for tracking both the burden and the risk for disease, and how they're calculated and what goes into those calculations. So that when you see these numbers in the media, in research articles, in your other classes, you know how they're calculated and what they actually mean, so that you have a better idea of how to interpret those numbers as well. So prevalence, and this is just to distinguish the difference between prevalence and incidence. Prevalence is just the number or proportion of people who have a particular disease out of the total population in a given time period. So for example, prevalence of HIV was, there were 1.2 million people in 2012 who had HIV in the United States. It's a measure of burden of disease, and we could calculate it as a percent as well, and say if I take that 1.2 million people who were living with HIV in the United States in 2012 out of the total population of just over 300 million people in the United States, the prevalence of HIV would be around 0.3 to 0.4% of the population. So as a whole, HIV does not have a large burden in the general population, and the prevalence is very low. But that only gives us part of the picture, and we will need to know in subpopulations, in different racial ethnic groups, in different groups by sexuality and gender identity, what is the prevalence of HIV and why is it different? And so there's ways that prevalence can be used to say this is the burden as a whole, but we still need to separate it out by different subgroups of the population. Incidence, on the other hand, is the number of new cases of disease in a certain time period. So for example, incidence of HIV in the United States in 2012 was 50,000 cases. So there were just 50,000 new cases of disease. That's the basic count number. We can calculate that as a rate and say there were 2 new cases of HIV for every 100,000 people in the population in 2012 in the United States. So this tells us a measure of disease risk. Essentially, it tells you what is the rate of new disease in the population in that time period. The higher the rate of new disease in the population in that time period, the higher the risk is for people getting that particular disease. So prevalence is a measure of burden, incidence is a measure of risk of disease. So there are formulas that are associated with these, and we'll walk through some examples for these. using a figure that you're going to see quite often. But prevalence is just the total number of people with that disease on that particular day that you're doing the calculation for, or in that particular year, over the total population. And it's usually interpreted as a percent. So typically I'll ask you to just give me a percent. Prevalence of SARS-CoV-2 is 10%, prevalence of HIV is 0.4%, or whatever the disease is. Incidence is the number of new cases of disease in a given time period over the total population at risk. And there are actually two different calculations for incidence. There's one that we call incidence rate, and there's another that we call cumulative incidence. If you'll notice, for the incidence rate, it gives it to me out of the total person time at risk. We're going to talk about in just a moment what that total person time at risk means and what person time is. And then our cumulative incidence is just out of our total population at risk as a whole. And so it basically means who is at risk of developing the disease or of getting the disease overall. So that definition of what it means to be at risk for a disease becomes an important part of our calculation for incidence. So I want you to think about, when you're thinking about calculating either incidence rate or cumulative incidence, what does it mean to be at risk for disease? So for example, if I'm thinking about something like HIV, people who are at risk for HIV are those who already are not infected with HIV. So we don't have a vaccination. And then the other people who are not at risk for HIV or are at very, very minimal risk for HIV are people who are on PrEP or a prophylactic, so a prevention tool that can prevent HIV infection. Has anybody ever heard of PrEP? Or how many people have heard of PrEP for HIV? And I only ask this just out of curiosity, because it is something that unfortunately not enough people have heard about or know is an available prevention tool for HIV. See, one, I have not heard of it. I have, no. Okay. So PrEP or pre-exposure prophylaxis, you've maybe seen commercials for it. There's Truvada and there's Descovy are the two common ones that you see a lot of commercials for. It's essentially a singular pill that a person can take that reduces their risk of getting infected with HIV by about 99%. So if someone is thinking that they might be at risk of getting infected with HIV, if they take that pill every day regularly, then their chance of getting infected with HIV is almost nothing. So it's a really good prevention tool for prevention of HIV as a whole. And it's something that we need more education about and more people to be aware of, so that we can continue to prevent the spread of HIV to get our incidence to zero. And that's the goal globally, and in the United States especially, is to move to zero, to where we have no new cases of HIV happening. And I think the goal is to have that happen within about the next 10 years. But we have a lot of work to do to get to that point. And so really the goal is to get our incidence down to zero. And so one of the things you have to think about, and there's a little bit more information about this in the recorded lectures, is who is at risk for disease. So when you're thinking about calculating that incidence rate or cumulative incidence, you have to exclude anyone who is immune to that disease for some reason. Maybe that's because they've gotten a vaccination and now their risk of, and you're assuming that that vaccination is 100% effective at preventing actual disease, which we can talk about a little bit later, or they've already had it and that disease can't reoccur, or they're not at risk for it because it's not a disease that affects their subgroup of the population. So for example, if I'm calculating an incidence rate for ovarian cancer, I would exclude all biological males because they're not at risk for ovarian cancer. And so we need to make sure that we're excluding the right people from our total population at risk. But what I want to focus on here is the total person time at risk, because this is the one that is often the most confusing for students in terms of how do we calculate that total person time at risk. So let me see. So I'm going to attempt, oh, that's not great. My iPad's not working. Normally I'll go through sample problems using my iPad, but it's not letting me pull it up right now. So I'm going to attempt to use the annotation tools to go through some examples on Zoom itself on my computer using my mouse. So I apologize in advance for how scribbly my handwriting might be using my mouse. I'm going to do my best to make it clear. So this concept of person time that we have in our formula for cumulative or for incidence rate, what person time is an estimate of the actual time at risk that a person has for that particular disease. And we calculate that in years, months, or days, or weeks, or whatever it is that is, sorry, my cat just knocked down something on my desk like cats do. And so we calculate it in the time frame that is most relevant to that particular disease. And what it tells us is how much time a person is contributing in our research study. So we are typically calculating this in a research study to being at risk for a particular disease. So you can also call it person years, person months, person days. And to go through a quick example, so 100 person years. So say we have 100 person years in our research study that we are using as our denominator for our incidence rate calculation. 100 person years can equal 100 persons followed for 1 year. So what that means is that we have 100 people that we're following for 1 year of time. They've each contributed 1 year to being at risk for that particular disease. So that equals 100 person years. It could also equal 50 persons followed for how long? So if I want 100 person years, it could be 50 people. Kevin, I see you holding up your fingers. 50 people followed for 2 years. So basically that means that each of those 50 people are at risk of the disease for a total of 2 years that we are following them forward. It could equal 1 person followed for how long?
100 years.
100 years. So this all in our denominator of our incidence rate, it could be 1 person followed for 100 years. That's the equivalent of 50 people followed for 2 years, 100 people followed for 1 year, or it could be how many people followed for 6 months.
200.
200 people followed for 6 months because each person is contributing 6 months at risk for that particular disease. So what this gives us is a measure of risk saying that if I follow 100 people for 1 year and they're all at risk, that is the amount of time that those people could have potentially gotten infected with that particular disease. Now, as you can imagine, this is a very simplified version of what person time is. What you are going to be expected to do, and we're going to walk through this particular figure and how to use it to calculate person time, how to calculate incidence rate, how to calculate prevalence, and so on together right now. But I'm going to tell you right now, you are going to see this figure on your homework, number 1. You are going to see this figure on your exam. You will likely see this figure on your final exam as well. And what it is going to be is this exact same figure, but what will be different is where these arrows and red lines and crosses are located. And we'll talk about how that impacts the amount of person years that we are calculating. So What we're looking at here, and I'm going to kind of go through details of what this figure represents. This figure, first off, we have a population of 40 persons. So there are 40 people in our population as a whole, as indicated right up here in the description of this figure. The figure itself represents 10 new cases out of that population of 40 people. And so that means that at some point in this time period, given in this figure, that those 10 people got sick with whatever disease it is that we are interested in calculating prevalence and incidence for. And we are going to assume that all of the healthy individuals that are not included in this figure, so that means that there are 30 people that are not included in this figure, that they're at risk for this disease that we're calculating prevalence and incidence for. Each horizontal line, each red line, represents one person, as indicated also on the left, where it says 1, 2, 3, 4, 5. A down arrow indicates that that person got sick. An up arrow indicates that that person recovered. And a cross indicates the date of death, meaning that they died from that particular disease. This disease can reoccur. So meaning that if someone gets sick and then they get better, they can get infected with that disease again and get sick again. So what we want to do is determine the incidence rate of disease per 1,000 person years. So if you remember, my incidence rate, you can see me typing, right? Equals number of new cases over person years at risk. And we want to calculate that from October 1st, 2014 to September 3rd, or 2004 to September 30th, 2005. And so what is the incidence rate during that 1 year period? The first thing that I need to do to calculate the incidence rate during that 1 year period is I need to calculate the number of person years at risk for that disease. So using this figure to calculate the person years, first what I'm going to do is I'm going to go back up, and it tells me I have 40 persons in my population. They're people who are not in this figure. They're all healthy for that entire time period. So that means I have my N equals 30 who are not represented in this figure. They're each at risk for the disease for 1 year. So that means those 30 people contribute 30 person years at risk for the disease during that 1 year period. Does that make sense? Is that somewhat clear? So we have 30 people who are not represented in this figure. It tells me we're assuming they're all healthy and at risk of getting the disease. We're calculating person years for that 1 year. So that means those 30 people times 1 year equals 30 person years. Cool. So now I need to calculate person time or person years at risk for the 10 people who are represented in this figure from October 1st to September 30th. So what I'm going to do is I'm going to count up the amount of time that each person is at risk for the disease, or essentially when they don't have the disease or when they haven't passed away, to first get the number of person months and then convert that to person years. So I'm going to put months here. Wow, that is terrible. I apologize. So person one, if we are looking at how much time at risk is how much time is person one at risk for this disease from October 1st, 2004 to September 30th, 2005, essentially what I'm going to do is I'm going to count these number of boxes. So on October 1st, they're disease free. They're at risk for this first box. Then they get the disease. They have the disease for 4 months and they pass away. So this time they're no longer at risk because they're not alive. So they're not at risk for the disease. So person one is at risk for the disease for 1 month. during that 1 year period. Because for 4 of the months, they have the disease, and for the rest of the time, they're no longer alive, so they're not at risk. Person 2 starts out disease-free. They're at risk for 1, 2, 3, 4, 5. Then they get the disease, they're sick for 2 months, and then they pass away. So none of this time afterwards counts because they're no longer alive, they're not at risk for disease. So person 2 contributes 5 months at risk for this particular disease. Hopefully you're starting to see how I'm calculating this. So how much time at risk is person 3 for this particular disease? And it's probably a little bit harder for you all to see because you're looking at it on a screen and I don't know how big it is on your side. So the first month I have a chat, the first month over here, that's not included because I'm calculating it from October 1st to September 30th. So this first box is before the time period that I'm doing my calculation for. This last box over here is after the time period that I'm doing my calculation for. So when you see things like that, that's where it's important to think about what is that time period that I'm doing my calculation for. And in this case, it's just between October 1st and September 30th. So person 3, I see from Kevin, contributes 10 months. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So they contribute 10 months at risk. What about person number 4? 11 months. Yep. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This one doesn't count because they're sick, but then they recover. Person number 5. 3 months. What about person number 6?
5 months.
5 months. So 1, 2, 3. One thing to be mindful of when you're looking at these, don't forget the couple of months there afterwards. So making sure you're looking at their recovery status, whether or not they recovered or they passed away. Because if they recovered, they're at risk again. What about person number 7?
7 months.
So 1, 2, 3, 4, 5, 6, 7 months. So is everybody seeing the pattern of how we calculate the number of months? So person number 8 is 11. Person number 9 is just 1. None of this afterwards counts. And person number 10 is 0 because they start out sick. They're sick for 11 months and then they pass away. So that month doesn't count. So now, oh yeah, go ahead.
Sorry, I had a quick question. Since not all diseases are can be reinfected, do you want us to assume, at least for calculations, that they're still at risk?
I will tell you that in any scenario that I give you. So if it says that once they recover, that they can get sick again, and I told you that in my description, it doesn't say it in this particular scenario, then that means that you would count those months after. If it said when they recover, they are now immune to getting that disease again, you would not count those disease after, those months after, because they're not at risk for that particular disease.
Okay, thank you.
Yeah, so that's where that at-risk definition becomes important, and thinking about what does it mean to be at risk. If someone's had the disease, are they at risk? Or, and I'm not going to do this to you all, but say I put something here where it's like they got vaccinated on this date and that vaccination prevents disease completely. So now none of those months after that date of vaccination would count because they're no longer at risk for that particular disease anymore. So that's where it's important to clearly define for that particular disease that you're doing their calculation for, what is that at risk mean and how are we calculating this amount of person time. So then, now that I've gotten the number of months that each person, each of these 10 people represent as being at risk, then what I do is I add all of these up. So I have 6, 16, 27, 28, 29, 35, 42, 52, 53, 54. Hopefully my math is correct. If not, someone correct me. I'm terrible at basic math. So 54 months that are contributed by these 10 people. Now, I want this in person years. So in order to convert that over to person years, you have to then divide that by the number of months in a year. So then I would take 54 and I would divide that by 12. And so 54 divided by 12, let's see, I can't do that in my head.
4.5.
4.5. So then, okay. So that is the amount of person years that these 10 people contribute. And then I have 30 person years that those other 30 persons contributed. So in order to get total person years, I need to do 30 plus 4.5, and that equals 34.5 person years. Now that becomes my denominator for my incidence rate calculation, which, if you remember, is the number of new cases over person years at risk. So if I want to calculate the incidence rate, that's going to be first, I have to do what are my number of new cases during that time period. So in order to get the number of new cases, that's all the down arrows, because the down arrows is onset of illness. So I go and I count those down arrows. There's 1, 2, 3, 4, 5, 6, 7, 8. The 2 down arrows that occurred before October 1st, 2004 don't count because those were not new cases of disease during that time period. So there's 1, 2, 3, 4, 5, 6, 7, 8 new cases of disease divided by my number of person years, 34.5. And so that gives me 0.23188. And then I have to multiply that by my multiplier. And in this case, that is 1,000 person years, as I indicate up here above. So that gives me let's see, that's times 1,000, that equals 231.88. So that tells me my incidence rate of disease is that there were 231.88 new cases of this disease in this population per every 1,000 people in the population. So that's the method that you'll use to do that calculation. Are there any questions about that?
Yes. So if one person got the disease, recovered, and then got that again, we would also count that down arrow in the new cases?
Yes, exactly. So say, for example, on this figure, there was another down arrow right here because that person was unlucky, and 2 months after they recovered, they got sick again, and they were sick for another 2 months. Then that would mean that that down arrow, that's another new case of disease in that particular time period. So you would count that again.
Cool, thank you.
Mm-hmm. So what I would like you to do is you have exercise number 1. Part B is essentially this figure. The other thing it's going to ask you to do is calculate prevalence. So remember, prevalence is the number of existing cases of disease on that particular day over your total population on that day. So I'm not going to go through that exactly, but I want you all to think through who is your total population. So if I'm calculating prevalence on September 30th, 2005, how many people are in my population on September 30th, 2005? Related to that, when I say on that particular day, if a red arrow overlaps with that date that I'm asking you to do the calculation, the red line, that indicates that they're sick on that particular day. So for example, on September 30th, there in this particular figure, there's one person that is sick. So I'm going to put you into some breakout rooms. I'm going to give you about 10 minutes to work in your breakout rooms to go through exercise number 1, part B, to make sure you're all feeling comfortable with going through and calculating the number of person years, incidence rate, and prevalence as well. If you have any questions while you're working through them, go ahead and let me know, and I will jump into your room and answer any questions that you might have. Or you can jump back out into the main session and I will answer questions that you have there. So like I said, I'm going to give you about 10 minutes. So we'll come back at around 10:25. We'll quickly review that and then we'll talk some about infectious disease epidemiology. So I'm going to open all the rooms, go through the example. Let me know if you have any questions. All right, welcome back, everyone. Hopefully you had enough time to get through at least most of that. As I said, so we'll go through the answers right now, but also, as I said, you are going to be expected to be able to do that on homework number 1. You're going to be expected to be able to do something like that on the exam. So if you, after this live lecture, after watching the recorded asynchronous lectures, there is a recorded lecture that walks through a very similar, if not the same example that you're all doing right now. If you're still not comfortable with doing these calculations or understanding what they're meaning or how to use them, please don't hesitate to reach out to me, because you're going to see this on your exam. And it'll be about 10 points of 100 points on your exam. So it should theoretically be something that you're all really comfortable doing by that point, because you know it's going to be on there, you've studied for it, and you can zoom through that particular problem. So if you're not comfortable with it, let me know so that we can meet separately, or if there's a group of you that have more questions, let me know and we can go through it. So first question that you had to answer: what was the prevalence of disease on April 1st, 2005? So what is our prevalence? Prevalence equals number of existing cases over pop at risk. So in this case, what was the prevalence of disease on April 1st, 2005? So if you look back, nope, wrong direction. Apparently that's going to stay there. So how many cases of disease were there on April 1st, 2005?
Seven.
There were 6. So 1, 2, 3, 4, 5. Can you all see my mouse when I go down? Okay, cool. So whoops. So this one here with the cross, that person died on the last date of the previous year. So they don't have the disease on that particular day. And I believe it should say that in the scenario on your exercise. So there's 6 cases. What is my population size, my denominator, on April 1st, 2005?
Would it be 40 minus the 3 people that died?
Yes. So it is not 40, because on April 1st, there are 3 people who died before April 1st. So they're not part of your population on April 1st, 2005. So they would have to be excluded from your calculation in order for it to be accurate. So then my prevalence is equal to 6 divided by 37. And that is going to equal something 16.21% or 16.2%. So on April 1st, 2005, the prevalence of disease was 16.2%. And when you do that calculation, it gives you 0.162. And I just multiplied it by 100 to get a percent. So does everybody see where we got the 37 and the 6 from? So again, with this, most important thing is ensuring that you're looking at who had passed away before that particular date that you're doing your calculation for. Anyone who passed away before that date, you're removed from your population. Okay. So then how many person years are contributed from October 1st, 2004 to September 30th, 2005? So were any groups able to calculate the number of person years? So how many person? Okay, go ahead.
We calculated a total of 31.75 person years.
So 31.75 person years. Is that what others got as well?
I got that as well.
So I'm not going to go through the whole thing, but in order to come up with that again, so remember person 1 contributes 0 months, person 2 also contributes 0 months because they're sick the whole time, or the person 2 is sick and then passes away. Person 3 contributes a total of 9 months, and so on. So you would just go down, you would add those up and divide by 12. So then the number of person years is that 30 that are not included in this figure, plus the 1.75 that you get from going through this calculation. And then my incidence rate calculation is new cases over person years. So how many new cases of disease did I have during that time period? Six divided by 31.75 is my number of person years. So then that would give me 0.1888. Multiply that by 1,000 for my multiplier, and that gives me 188.97 or 188.9, or however. Like I said, I'm not very a stickler on rounding. And so my incidence rate of this disease from October 1st, 2004 to September 30th, 2005 is 188.9 per 1,000 persons in the population. How are we all feeling about that? $50-50. Hey, that's not too bad for it being the first time that you've probably gone through it, and that we're seeing this. This is one of those whole brand new concepts that's kind of an odd concept that most people have never heard of before coming to an epidemiology class, thinking about person years. But just remember, so person years, it's the amount of time that the people in your study or in your population contribute to being at risk for this particular disease. So when we're thinking about incidence of disease, that incidence of disease is changing based on the number of people who are at risk, and the number of people in our population and so on. So again, that's why those denominators, when you see things in the media interpreting incidence or prevalence of disease, what I always am going to encourage you to do is think about, well, out of whom are they doing this calculation? What is their denominator? Because if they're using the wrong denominator or population size, or making comparisons between populations based on different information, that's not going to be an accurate representation of what those disease patterns actually look like in the population of interest that you have. So your population at risk, your total population, for all of these calculations, whether it's morbidity or mortality calculation, are extremely important for what these numbers actually mean. So, and there's a lot of uses of incidence and prevalence. As I had said before, prevalence tells us the burden of disease, overall burden of disease in the population. So basically what that tells us is if there's a higher prevalence, that means that we're facing a larger problem from that particular disease in the population. Incidence tells us risk of disease. As our incidence, as our number of people out of the number of people with the disease out of the total population at risk increases, that means that the overall risk in our population is increasing. So as we see the incidence of COVID-19 increasing, because of its fairly easy to spread from person to person, that means that the overall risk in the population increases. And that is also a big clue on whether or not there's an epidemic. So that epidemic meaning that as our incidence increases, that tells us whether or not we're seeing a problem in that particular population. If prevalence is a lot higher than incidence, that means that people are either living a long time with the condition. So for example, with most chronic diseases like diabetes, like heart disease, our prevalence is typically much higher than our incidence because typically people live for many years with those particular diseases. If prevalence and incidence are similar to each other, that means that we are either people are either dying quickly from that disease, so they're not living for a long time, or they're recovering quickly from that disease. And it would be important to know what's going on. Are people dying quickly or are they recovering quickly? And so that means that there's not going to be a buildup of prevalent cases of that particular disease. So this is just a depiction of incidence and prevalence, kind of how they're related to each other. And then just to kind of finish up on this section, these rates that we've been calculating in these proportions, these are important tools in public health and in epidemiology to describe patterns of disease in the population. Understanding the numbers that goes into prevalence and incidence and mortality rates is important for doing comparison and for allocating resources, understanding health disparities, and then eventually, so this is all descriptive epidemiology that we're talking about, eventually doing analytic epidemiology to determine the actual why and how these rates of disease are happening, or we have a high prevalence of disease in a particular population. So then that gets us to analytic epidemiology, which we'll start talking about next week. So I had a thing in the chat, how do we get 6 for the new cases? So that, if you're looking at this figure again, so we're looking at the number of new cases from October 1st to September 30th. So we count the number of down arrows in that time period. So there's 1, 2, 3, 4, 5, 6. All of these down arrows that are before October 1st, 2004, those new cases of disease happened before the time period of the calculation. So they're not included in our calculation because it's not within that time that we are interested in. So hopefully that helps explain that. Okay, so for the next 25 minutes or so, I'm going to briefly talk about infectious disease epidemiology. Again, there are some recorded lectures for all of this content. So this is just meant to kind of be a review. And if you have questions about things, I have some slides specifically on COVID-19. So I'll go quickly through some of my others because that example took us a little bit longer than I was expecting it to, but that's okay because I want you all to be comfortable with that. So again, if you're not comfortable with person years and incidence and prevalence, please let me know and schedule a time to meet with me or schedule a time to meet with some of your classmates to ensure that you're comfortable with those. So infectious disease epidemiology. So we've talked about just epidemiology in general. We've talked about social epidemiology. Now we're talking about infectious disease epidemiology. Later in the semester, we'll talk about chronic disease epidemiology as well, or non-communicable disease epidemiology. What makes infectious disease epidemiology unique is that there are a lot of differences in the way that infectious diseases spread in the population than non-communicable or chronic diseases. And so understanding disease patterns and disease transmission is important for determining the cause of disease and for implementing prevention measures to prevent the spread of disease in the population. And one thing that I will mention is that most epidemiologists are not trained in infectious disease epidemiology. And the reason that I am saying that is because what we have seen happen in the last year with the pandemic is that there have been a lot of people who claim to be infectious disease epidemiologists in the media who have talked about COVID-19 when they actually have never been trained in the principles of epidemiology from infectious diseases. That is important because infectious diseases are very distinct from chronic diseases. There are things that are similar, but disease transmission, modeling, spread of disease, all of those things are very difficult to understand and are different from infectious disease to infectious disease. So what I've seen happening in the media about COVID-19 is that there has been a lot of misinformation about COVID-19 coming from so-called experts or epidemiologists that have actually misrepresented what this information actually means or how it can be used to prevent the spread of COVID-19 or other infectious diseases for that matter. Some of the major differences for infectious disease epidemiology, one of the major things is that the cause of the disease is often known or almost always known. So what that means, for example, for COVID-19, the disease, which is what we call when somebody gets infected with SARS-CoV-2, the virus, that we know that the cause of COVID-19, the disease, is the virus SARS-CoV-2. We know the cause of AIDS or acquired immunodeficiency syndrome is someone being infected with the HIV virus or a human immunodeficiency virus. So that understanding of that particular causative agent, that virus or that bacteria, and that how that leads to disease is unique in infectious disease epidemiology. Because with many chronic diseases, and this is something that we will start talking about next week, for things like diabetes, there is not a singular cause of type 2 diabetes. Rather, with most chronic diseases, we have what we call these multi-causative disease models, where for any particular case of type 2 diabetes, one person might have been physically inactive, have a family history of diabetes, been a smoker, and be older age, whereas another person might have had a poor diet, been older age, and had another comorbid health condition that's leading to their type 2 diabetes. So actually determining causes of disease for chronic diseases for individuals can be very challenging. But with infectious disease epidemiology, we know if we eliminate the SARS-CoV-2 virus, we will eliminate cases of COVID-19, the disease. Same thing with HIV, same thing with the flu, the cold, all of those other things. What is also unique with infectious disease epidemiology is that a person who is a case, so you've been infected with a virus or bacteria, that person now becomes an exposure. So if I get infected with, or if I get the flu, now if I come into contact with other people, and you can see this on the bottom here, so if I'm the primary case with the P, then I can expose other people to that pathogen as well, or that disease-causing agent, and then they can become infected. So now what that means is that the number of people who can infect others increases, and that changes the disease patterns based on the principles of that particular disease-causing agent or pathogen. And we'll talk about some of those numbers in just a moment. That is unique because with chronic diseases, if someone has type 2 diabetes, they are not going to pass on type 2 diabetes to another person by coming into contact with them in the same way that we do with infectious diseases. Now, I will say there is actually some evidence, and there's actually a lot of evidence, and we think about shared environments and behaviors, that those are shared by people. And so in a sense, somebody having type 2 diabetes, because of the environment that they're in, that can mean that kind of behaviors and things can pass on to other people and make them more likely, but it's very different than infectious diseases. Subclinical or asymptomatic infections can impact the epidemiology of the disease, meaning when we've seen this a lot with COVID-19, where about 40 to 50% of people, and that number changes all the time, are asymptomatic, meaning they have the actual virus, but they're not presenting any symptoms, but they still contribute to disease spread. How we come into contact with people plays a major role. So what type of spaces we're in, how crowded spaces are in, that plays a role in disease spread. Immunity is possible through vaccination or through getting infected, and that infection causing lasting immune response that prevents future infection. And there's sometimes or often a need for urgency. So we've seen that with the COVID-19 pandemic, in that we've seen a large number of people being hospitalized, being greatly infected by mortality in our population. So there's this need for urgency to curb the spread of disease. What we talk about with infectious disease epidemiology is emerging and re-emerging infectious diseases. And we see new infectious diseases all the time. And we see the re-emergence of old infectious diseases re-happening in different areas of the population. And so this is just kind of meant to say that re-emerging and emerging infectious diseases are changing all the time. And we actually, SARS-CoV-2 is a large pandemic and something that's been at the forefront of the media and of our public health response for the last year. But even during that time, we've actually seen the emergence and re-emergence of other infectious diseases at the same time. And so these are just some examples of emerging infectious diseases: SARS-CoV-2, chikungunya, Ebola, dengue, H1N1, HIV in the 80s, monkeypox, and there's many, many others. And one thing that I want to mention is that the majority of infectious diseases in human populations are actually of what we call zoonotic nature. So what that means is that the majority of infectious diseases that human populations are affected by are spread from animals to humans. So that as a result of the way that we interact with our environment and the way that we interact with animals in the environment. So examples like the current prevailing hypothesis is that SARS-CoV-2 was spread from animals, potentially in a wildlife market, to humans. HIV was spread from monkeys, so the chimpanzee and the pseudomangabe, to humans. Zika virus was spread from animals to humans. And this is generally as a result of the repeated contact that we have, and actually as a result of humans encroaching on environments, things like deforestation, things like our husbandry or animal practices, things like meat trade and consumption of meat, and our desire to continually consume more products and encroach on our environment. That means that we are interacting more with the animals and the other environmental factors that lead to us over time being exposed to those particular pathogens that are mutating, and then eventually will mutate to actually cause disease in human populations. So for example, in monkeys and chimpanzees and pseudomangabes, there is a virus called SIV, or Symbiote Immunodeficiency Virus, that was what is thought to have mutated to become HIV in human populations. SIV, which still exists, doesn't actually cause disease in humans, but that mutated virus does. And we've heard a lot about that with COVID-19, where we've seen mutations of that virus that have different principles. And there's a lot of discussion right now about how vaccinations and how current protective measures that are in place will also prevent the spread of those viruses that have slight mutations to make them more infectious or more pathogenic or other principles of infectious diseases. And so this zoonotic spread of disease is an important marker of health, an important thing that spreads disease in human populations. So we need to be mindful of how we interact with our environment, how we keep animals in like farms for meat trade, for milk, for things like that, and all of that, because that all contributes to disease in human populations. One thing I will mention is that the rate of infectious diseases has drastically decreased in the last 100 years. So what we have seen happening in most developed countries is what we call an epidemiologic transition, where the number of people with getting infected with communicable diseases and dying from communicable diseases, which is indicated by this top line going down, has decreased. If we look at this figure, shows mortality rate as higher. But what has happened is we have transitioned to non-communicable diseases, where the large killers in the United States and other developed nations are things like diabetes, hypertension, and other preventable chronic diseases. And so we've seen that change, but that is not to say, and we're living that right now, that infectious or communicable diseases are not an important driver of poor health and of mortality in the population. And we still need to continue to focus our resources, because in the last 5 to 10 years, we've actually seen a large increase in the number of emerging and re-emerging infectious diseases affecting human populations and leading to significant morbidity and mortality. So what we see happening in developing countries, especially countries in Africa, India, other developing countries in Southeast Asia, is they're facing really large dual problems with communicable and non-communicable diseases, where you have people, for example, with HIV and with type 2 diabetes or hypertension, or you have people who are infected with malaria and also have a chronic disease. And that complicates the way that we treat disease, that complicates the usage of different medications and how they can help with different populations and many other things. And so it's important that we continue to be mindful of the spread of infectious diseases in the population. I'm going to just quickly go through this. I'm not going to really test you on this, but some of the things that you all have probably heard about in the media about COVID-19 and some of the principles of infectious diseases are the reproductive number, the serial interval, and the incubation period. So the reproductive number for an infectious disease is essentially how many people a case will infect in the population. So if I'm infected with SARS-CoV-2, on average, how many people will I pass on that infection to? So for SARS-CoV-2, it's somewhere between 2 and 3. So for every one person who is infected with SARS-CoV-2, they will pass on that infection to 2 to 3 other people. The higher that reproductive number, the faster that disease will spread in the population, because it's spreading exponentially. And you can kind of see that in this figure on the bottom left. If one person passes it to 3, and then those 3 people pass it to 3 other people each, and then those 3 people pass it to 3 other people each, you can see that the spread of that disease is going to happen very rapidly. One thing that I want to mention is that this is in the absence of a vaccination in a what we would call an immune naive population, meaning that there's no immunity to that particular disease. As we develop vaccinations and as more people get infected with the disease, the reproductive number will actually decrease. If the reproductive number is less than 1, meaning that on average, each person infected infects 1 or less people with that disease, then the continued spread of that disease will effectively stop in the population, because there's not a continued transmission from group to group. One of the diseases with the largest reproductive number is measles, where measles in an immune naive population, on average, a person infected with measles will pass it on to 17 other people. So that means that one case of measles, 17 other people will potentially become infected. Those 17 people will infect 17 others, and so on. So you can imagine that in the absence of vaccinations, that measles could spread through our population very rapidly, which is why increasing the number of people who are vaccinated is extremely important. The other 2 ones here, serial interval and incubation period. The serial interval is the time between symptoms onset of the first person infected and symptoms onset of the second person infected. So the longer the serial interval, the more likely that a person is going to spread the disease to another person. So for example, serial interval of COVID-19 is anywhere between 2 and 14 days. So if it takes up to 14 days for a new person to exhibit symptoms, that might mean that that person, if they haven't gotten tested for COVID-19, they're going and interacting with other people and potentially infecting them, because many diseases, even without symptoms, you can pass them on to others. So that means the longer the serial interval, if it takes 14 days for someone to develop symptoms, they're out interacting with others, potentially infecting others, who are then interacting with others, and so on. For other diseases like the flu, the serial interval is 2 to 3 days. So that means if you come into contact with someone with the flu, the time from you coming into contact and getting infected with that virus and developing symptoms is 2 to 3 days. So there's the less time for you to pass that on to other people before you develop symptoms and know that you're sick. So that serial interval plays a role in the spread of disease, which is also why that if with COVID-19, if you come into contact with someone who has symptoms or who has tested positive, the recommendation is to quarantine so that you are not passing it on to other people unknowingly, even if you don't have symptoms or even if you test negative, because our tests are not perfect at detecting disease in the population. And we'll actually talk about principles of screening tests, such as those that we use for COVID-19 in the second half of the semester. And then the incubation period is the time from when a person gets an infection to the time they develop symptoms. And that can vary from disease to disease. So for like the flu, it might be 2 days. For COVID-19, it's about 2 to 14 days. For something like HIV, the incubation or latency period is a similar concept, is up to 10 years, where a person can get infected with the HIV virus, not have a clue that they've been infected, and then 10 years later start to develop symptoms of that virus. So then I'm going to kind of skip through some of this for the sake of time, because I don't want to hold this to after 11. But a couple of things that I want you all to make sure that you are looking through on the recorded lectures is there's talk about the epidemiologic triangle and the chain of infection. So these are two things that we use in infectious disease to understand how disease spreads from a host or a person, the who of it, who has the disease, through the environment and what that disease causing agent is. So with this epidemiologic triangle, if we get rid of the disease causing agent, which can be a bacteria, a virus, a parasite, or something else that's similar, then that means that we're going to stop the spread of disease in the population. If we get rid of the susceptible human host, so by vaccination, by quarantine or isolation, then that means we're going to stop the spread of infection. If we take care of environmental factors that allow for that disease to spread, so for example, with mosquito-borne illnesses, if we prevent there being reservoirs like standing bodies of water where mosquitoes can lay their larvae, then we will prevent the number of mosquitoes in the environment and prevent the spread of mosquito-borne illnesses, because we'll get rid of what we call a vector, and a vector, in which I'll show you actually on the next 2 slides from now. A vector is an animal or an insect that can spread disease from the environment to humans or from human to human. So one of the most common vectors that we hear of is mosquitoes. There are a large number of mosquito-borne illnesses like malaria, like Zika virus, where if you get bitten by a mosquito that has Zika virus or malaria, they can pass that virus on to you, and then you will get infected with that particular disease. So that is a form of what we call indirect transmission, where there are different types of disease transmission. There's vertical and there's horizontal. Vertical transmission means from an individual to their offspring. So that typically means from mother to baby. So there are a number of diseases that can be passed on from mother to baby in utero or during birth. So for example, if a mother is infected with HIV, all women, when they become pregnant, have to get tested for HIV. It is a requirement in the United States and in most countries globally. The reason being is that if a mother is infected with HIV, that baby will not become infected with HIV while in utero. But what can happen is during the birthing process, with the presence of blood, that baby can become infected with HIV during birth. And so if a mother is found to have HIV while pregnant, she will be put on medication or antiretroviral treatment to suppress that virus. So it's no longer a risk factor to pass on from mother to baby during birth. And so that's why we do screening for HIV for pregnant women. And that what that has done, especially in developed countries like the United States, is reduce the transmission of HIV from mothers to their children to almost zero. So we have very few babies born with HIV in the United States because we have the means to put women on antiretroviral treatment while they're pregnant and effectively minimize or eliminate that risk of spread of that disease during the birthing process. So that vertical transmission. Horizontal transmission has two different forms. There can be direct horizontal transmission, which means direct contact from person to person. So that would mean that I have the flu or the cold, and we come into contact either through sneezing or touching hands, or through sexual intercourse, or through some other means of direct contact with a person. That's a fairly common method of transmission, and social distancing is a way that we eliminate direct contact as, or minimize direct contact as a means of disease spread. So if a disease spreads easily from people contacting each other, if you social distance and you prevent that direct contact, you can effectively minimize or eliminate the spread of that disease. Other ways are things like masks and other things. Indirect contact or indirect horizontal spread of disease is either through some common vehicle like food or water, meaning our water is contaminated, or you get food that hasn't been properly prepared or has been left out, or through some environmental interaction, or through a vector, such as an animal or an insect like mosquitoes or mice, which are mice and rats are another common vector to spread disease. So indirect contact could be something like a virus has become airborne, meaning that somebody was in a room, we were breathing in that room. In their breaths, there are particles, and there are really small particles that can harbor virus that can linger in the air and become aerosols. There is actually really varying definitions of aerosols, but really it has to do with the size of that particular particle. So the difference between an aerosol and a droplet is aerosols are just much smaller and can become suspended in air. The smaller they are, the longer they can become suspended in air. So say someone had a cold and they're in their doctor's office and they're breathing, and that can become airborne. And then you go in and you breathe in that air that has those viral particles in it or those bacteria in it, then now you can become infected even though you had no direct contact with that person who was in that room. We know that for SARS-CoV-2 or for COVID-19, that it can become aerosolized and that it can infect people who are sharing space, but maybe are not in direct contact. So you go to the grocery store or you go somewhere else. So that's where masks come into play. That's where limiting your time in public spaces, especially indoor enclosed spaces without good ventilation, come into play to prevent that breathing in and coming into contact with those aerosols. The difference between an aerosol and a droplet is a larger particle. So when you respire or breathe, the droplets will fall to the ground within a shorter distance. They estimate about 6 feet. Some droplets, depending on how hard you're breathing, like if you're running or exercising, they might travel a further distance. But then those droplets so if you're close contact with somebody, that might be a more direct contact because you've actually been in contact with those droplets. So say someone sneezes on you, that would be pretty much a form of direct contact because they've sneezed on you. An indirect form of contact for disease transmission from droplets might be through the environment and what we call fomites. So someone sneezes on the desk, and say we're in person in a classroom. Someone is sick, they're sitting in the classroom before you are, they sneeze or they're touching their nose and their mouth and they're touching the desk in front of you. And then you go and you sit down at that desk unknowingly that they were sick before you touch it, and then you touch a mucosal membrane, meaning your eyes, your nose, or your mouth, or other regions as well. And then that transfers that virus or bacteria into you as a susceptible host. That is a form of indirect contact. So common ways are through like door handles, through desks, through chairs, through shared things that we use in classrooms and our jobs and other places. So that's where disinfecting things becomes very important for prevention of spread of disease. So as you can see, there are many different avenues for infectious diseases to spread from person to person, either via vertical or direct contact or indirect contact, that horizontal way. And so that's why it becomes very challenging to prevent infectious disease spread, is because it takes a large number of people to interact together to do that. And so we're just past 11, so I'm not going to go through all of this. I'll pick up on some of this next week, because next week's content is much shorter than this week's, and I realize I'm kind of running out of time every single week. So I apologize. I'm definitely not managing my time well to make sure we're getting through what I want to in these live sessions. I'll do better moving forward. So I'll go through some of these other things for infectious disease epidemiology, and we could talk specifically, and I'm happy to stay longer if anybody wants to talk about COVID-19 or anything else. But I did want to talk specifically, and some of you may have seen this particular figure circulating online. One of the things that we think about when we talk about prevention of infectious diseases, and this figure particularly is for respiratory diseases like COVID-19, is that no singular prevention measure is 100% effective at preventing the spread of infectious diseases. Instead, we have to have multiple layers of prevention that happen at both the personal and the shared or the environmental level or infrastructural level to help prevent the spread of disease. So if we think about the different layers for preventing COVID-19 or the cold or the flu or other respiratory illnesses, first layer might be, if you're sick, you stay at home, you physically distance from people. That's a problem in our population because many of us don't have sick pay to stay home from work, or we are actually often encouraged to go to work when we're sick because you don't want to fall behind, or your work needs you, or some other reason, or you need the money and you don't have sick pay. So that becomes a problem, but that is the public health message. If you're sick, stay home, because that means if you go to work, you're gonna pass it on to other people. Then next level of prevention might be masks. Use masks to prevent that the air that you're breathing from spreading on to other people. Hand hygiene, coughing etiquette. So washing your hands frequently and properly for 20 to 25 seconds, using hand sanitizer, not coughing into your hands, but coughing and sneezing into your elbow or into your shoulder. Avoid touching your face. And that's an important one, and something that I struggle with is touching your face too much, because if you touch a surface that has a potential pathogen on it, and then if you wash your hands and there's no avenue for it to enter your body, that it was not going to spread from person to person. But if you touch a surface that has a pathogen and then you touch your nose or your mouth or your eyes, you've now given it a portal of entry or a place to enter your body to potentially cause infection. If you're in a crowded space, limit how much time. So limit where we are in grocery stores, especially if we're potentially sick or exposed to people who are. Those are things that we can do on an individual level. But on a shared level, and where our infrastructure is failing right now, especially with COVID-19, are things like having available, fast, sensitive, and inexpensive, cheap, or free testing so that everyone can get tested and know their disease status, and that's an accurate disease status, so that when we are going out into public spaces or meeting with other people, we know what our disease status is based on regular testing. That is not always happening, and that hasn't happened on a regular basis for COVID-19 in our population throughout the last year. Having good ventilation, and this is very important for aerosolized diseases like COVID-19 or the flu or the cold, where having a good air conditioning or HVAC system that has good filters, that air, as it's being circulated through the rooms, that if there are viruses or bacteria in that air, that it's being filtered out and there's new clean air moving through those spaces. What we know throughout the United States, in many hospitals, in many schools, in many other public buildings, is that our HVAC systems or air conditioning systems are highly inadequate. They're outdated, they're old, they don't have the proper tools and machinery to filter that air to protect the people who are in those spaces. So that means that if there's not good ventilation in the indoor space and people come in who are breathing, who potentially have an infection, if that air is remaining in that space, everyone who comes into that space is potentially exposed to that air that's unfiltered and that's circulated or remaining in that space. So having good ventilation and air that's circulating through spaces from good HVAC space things, or being outdoors, or having windows open can be a way to prevent the spread of disease. We also need governmental messaging and financial support, and we need the ability to quarantine and isolate. So if someone does test positive for disease, they need to be supported to be able to stay home from work so that they're not exposing other people. But we know that people in many industries, especially essential workers in grocery stores and restaurants and in other places, they don't get sick pay. There have been instances of people losing their jobs because they have said, I need to stay home because I'm sick. And then that leads to financial distress and burden, not being able to feed themselves and their family. So if we don't have financial support for people to be able to quarantine or isolate because they're either sick or exposed, potentially exposed, then we're going to have people who potentially have disease interacting with others and spreading the disease. And then that last form of prevention is vaccination and other, so we have that with COVID-19 happening right now, where there are vaccines that they're pretty effective. And so we need to ensure that those vaccines are getting to the right people, that there's a good dissemination plan, and that we are addressing things like vaccine hesitancy and people not wanting to get the vaccine. So currently, most of the surveys that have been done in the US have showed only about 50% of people in the US have said that they are willing to get the vaccination against COVID-19. That is not enough people to actually develop what we would call herd immunity or community immunity, so that we can limit or prevent the spread of disease in the population. And there's actually a lot more that goes into that, but we need to have messaging and tools and availability so that people can get the right education to know about how the vaccine was tested and its safety. But we also need to ensure that people can get it when they want to. And that's a big problem we're facing right now, where there are lots of people who want to get the vaccination, but they just can't because its availability is low. Or a larger problem that I'm seeing happening is that scheduling an appointment to get a vaccination is extremely difficult and discouraging. And especially people who are elderly or with limited internet access or limited resources, people being able to get an appointment for a vaccine can be nearly impossible if they don't have adequate resources or people to help them navigate the systems that we've put into place. So that's a problem in our infrastructure that we've set up in order to roll it out. So these are, for something like COVID-19, these are all the things that need to be put into place for us to be able to resume whatever a normal life might look like, and for us to be able to prevent the spread of disease, prevent morbidity and mortality from COVID-19. But many of these are not happening consistently throughout the population, and they're not happening regularly enough in order for us to be able to be comfortable from a public health perspective to open things up all the way to protect our population. And there's a lot that goes into those decisions. And I'll say, have the right decisions been made throughout this last year? Absolutely not. There have been a lot of things in their responses to COVID-19 that have been completely botched, and that shouldn't have happened, or that could have happened, that didn't happen, that could have led to us being in a much better place than we are in right now. But what we can't just reflect on the past. We need to learn from those things and think about how do we move forward to get a good vaccination rollout, improve ventilation and HVAC systems, get better testing and reliable testing, get good messaging for why we're wearing masks and all of those things. And all of that has to be used together. Otherwise, we're going to fail at coming out of this pandemic, and we're going to fail at responding to future potential infectious disease pandemics as well, because we need to have that infrastructure available to support all of these things that need to happen. So I'm happy to stay on and chat more about COVID-19, infectious diseases. I'll chat some more about it next week as well, because next week I do only have a small amount of stuff to talk about, and we can have some discussion about some of these things next week too. But are there any questions or anything that you are wondering about at this point that I can answer? And again, apologize for not managing my time very well in some of these live sessions, because I'm going over and not getting through what I want to. So I'll do better about managing that time moving forward. So what questions do you have or concerns, or what do you need from me at this point? Nothing? Cool. All right. Well, hearing nothing, I hope you all have a great rest of your week. If you need anything, don't hesitate to reach out. I'll stay on here for a few minutes if anyone wants to chat about anything. But otherwise, have a great rest of your week and weekend. Work on homework 1. Reach out to me if you have any questions. I'll post next week's content later today, as well as your homework number 2, just so you have it early, but it won't be due for a couple of weeks. And I'll send you the regular reminder by Friday. And I will also post this recorded lecture by the end of the day today once it's processed and I'm able to get it up on Google Courses. So yeah, have a great rest of your week. Thank you all for sticking with me, and I will talk to you all soon.
Thank you, Professor.
Thank you.
Thank you, Professor.
Thank you.
Thank you all.
I have a question.
Oh yeah.